We have Plutonic Clast, and this is a gabbro clast in the lower part of Ignimbrite D. And this is an angular Plutonic clast, so obviously it wasn't liquid or mushy or anything. This was solid. This was brought up by the magma, and Ignimbrite D actually has a fair number of them. So where do they come from? Well, they come from what is known as the underplating zone, the area under the island where magma is stored before it rises up. And in that underplating zone we have a lot of crystallization. So this is where the magma is actually made into what it is that erupts at the surface, and we have these underplating zones in all the active volcanic islands in the Canaries. It's been shown seismically, and in some places we also have these plutonic suites. I have a master's student at the moment working on plutonic nodules in the Naga, which is the northern part of Tenerife, and there's some dikes that bring up some of these nodules, these plutonic rocks. So this is a window into what happens deep under the volcano. Actually, even below the ocean crust or within the ocean crust area, that's where these guys form. And this is also where the magma in La Palma came from that just erupted. They come from these underplating zones where the magma is stored, it fractionates, it gets richer in gas because of that until it's ready to erupt. And that's what feeds the eruption. So the magma in La Palma was shown to be present years ahead. The scientists knew the magma was there. The local people somehow didn't catch on to this idea. So for them, it came as a surprise, at least that's what they argue. It came as a surprise that La Palma can actually erupt in this fashion. I mean, for the scientists, it wasn't really a surprise. There was earthquakes years before. There was seismic evidence for an underplating zone. There was even lateral migration of earthquakes, meaning that there was lateral movement of magma. So scientists knew already for several years that there was something on the boil under La Palma, and therefore it wasn't a huge surprise. And these are the kind of evidences that help us understand what's actually going on down there, because there we have a plutonic record. So have a little look around. The other interesting feature here is, have a look at the size of the fiamme here. Can I just ask you to step aside for a second? Look at the size of this fiamme. So the aspect ratio, meaning the length relative to its kind of height, is really different to what we've seen so far. They have been extremely flattened. These were likely pumices or magma, frothy magma bits before, and look, how much do you need to squeeze them in order to get to this point? Whoa, so compaction here in the lower part of the Ignimbrite, really intense. And then the size of fiamme seems to kind of change a little bit higher up. So here in the lower part we had big froth of magma coming out, and here we have a few lithic clasts again. There we see some rotation in there, some compaction and rotation, and it opened up some spaces because of the rotation, meaning that there was still movement in that hot ash pile after the thing was deposited. There's very strong evidence for this. We call that rheomorphic flow, reforming, if you will. Once it had been deposited, it can still flow downhill. And if we go a little bit further, there's a flow unit boundary, and I recall that it had chopped off a fiamme from below the flow unit boundary, implying that the pulses come with erosional energy. They can actually take away some loose material on the surface. As we would expect, imagine there's a pyroclastic flow coming through, it would pick up material from underneath. It would erode some of the substrate, obviously, and it has a lot of erosion power, if you will. So this is Ignimbrite D. I'd say we spend 5 minutes here and then we make our way further up the hill. And what do you think is coming after Ignimbrite D? Anyone? Are you sure? I think you're right. Okay, let's do that.